In this tutorial, you're going to learn how to write the code for hardware implementation of parallel interface with STM32 timer and DMA. STM32F103C8 does not have a dedicated peripheral for parallel communication, but it is possible to implement it with timer and DMA without delay and with minimum CPU load. In this video, I'm going to write the code to run parallel character LCD with STM32F103, but the information you're going to learn in this video has lots of other applications. In the first part of this video, character LCD datasheet is explained and how MCU can communicate with this device and configure it. In chapter 2, which is short, I explained Arduino approach to interface parallel character LCD. Last and main part of this tutorial is writing code to interface character LCD with STM32F103C8 with no delay 2 times. First with data exchange in interrupt and second with DMA. Learn about LCD pins by looking at this slide. In parallel interface, there is a wire for each bit. LCD has a 8-bit wide bus and it has 8 pins for parallel bus, and I have to reserve 8 MCU pins for them. There are also 3 LCD pins for controlling parallel communication. LCD RW pin is connected to ground because I always want to write to LCD. For E and RS LCD pins, I need 2 MCU pins. LCD has a CG-ROM. This memory stores all characters that LCD is able to show. Each character has an 8-bit address. In CG-ROM default state, a character address is that character ASCII code. For example, uppercase A address is 65, which is uppercase A ASCII code. LCD has a second memory called DDRAM. I have a 16:2 LCD. It has 2 rows and 16 columns of character spaces. It has 32 character spaces and it can show 32 characters at the same time. For every one of these character spaces, there is a byte in DDRAM with a specific address. When you want to show a character in a character space, you have to write that character address from CG-ROM memory in character space address in DDRAM memory. In this example, I want to write uppercase A in this character space. This character space has a byte in DDRAM with address 01 and uppercase A address in CG-ROM is 65. If I want to show uppercase A in this character space, I have to write 65 in address 01 in DDRAM. I have to write 65 in address 01 in DDRAM. It's done in 2 steps with 2 instructions. First, I have to tell LCD the address that I want to write to, which is address 01 in DDRAM. Second step is writing 65 to LCD. This is the instruction for writing to LCD RAMs. An instruction specifies RS, RW, and 8 data pin status for doing a specific task. RS pin is high because this is a data instruction, not command instruction. RW pin is ground because I'm writing to LCD. And 8 data pins represent the byte that is being written to RAM. This byte is going to store in the address that address counter register holds. Address counter is an 8-bit register inside LCD and its value can increase or decrease automatically by 1 after each write to RAM. First step was specifying address to write to. This is done by writing the address that I want to write to address counter register. I want to write to address 01 in DDRAM. And I have to write 01 in address counter register. And because it's a DDRAM address, I have to use above instruction to write to address counter. Below instruction is for setting CG-RAM addresses in address counter register. Both of these are command instruction and RS is 0. There are 11 instructions. You already know these 3. In instruction table, you see instruction name, RS, RW, and 8 data pins status. For each instruction, there is a description of what this instruction does, and there is execution time for each instruction. Except for first 2 instructions, execution time is less than 45 microseconds. Last 2 are data instructions for writing and reading bytes to RAM. For these 2, RS is 1. For others that are command instructions, RS is 0. I'm gonna talk about 1 other instructions and you have to read the rest yourself. And that's function set instruction. This is a command instruction. RS is 0, RW is 0 because this is writing to LCD. Pin 7, 6 and 5 are 0, 0 and 1. For pins 0 and 1, there is just a minus sign. It means it doesn't matter what their value is. I put these 2 pins low, they are 0. Pin 4, 3 and 2 are DL, N and F bits. These are configuration bits. For example, when DL or pin 4 is high, it means 8 mode bus is used. When DL pin is low, it means 4-bit bus mode. If pin 3, which is N, is low, it means one line display mode is set. If N is high, it means two line display mode is set. When you're executing function set command, you have to write a byte to 8 data pins. This slide explains the process of making that byte. Here there are 4 definitions. First one is the base value for this instruction. It's bits that don't change. Bit 7, 6, 5, 1 and 0. And their value is 0, 0, 1. For bits that change, I put 0. And bit 1 and 0 are also 0. This is 20 in hex. And these 3 definitions are bit mask for bit F, N and DL. Now imagine you want to make a byte for function set. First you write LCD function set. This is the base value for this instruction. It's 20 in hex. You do bitwise OR with bit mask for bits that you want to set. In this example, I wanted to set N bit and DL bit. I wanted 8-bit bus mode and 2-line display mode. Now this is the byte that I have to write to LCD with function set instruction. This is the problem I'm going to solve with timer and DMA. This is timing for writing an instruction to LCD. Step 1, change RS pin. If it's a data instruction, RS is 1. If it's a command instruction, RS is 0. Step 2, make enable pin high. Step 3 is putting instruction value on parallel bus. And step 2 and 3 order can change. And last step is make enable pin low. This is step 4. When you make these pulses, you have to meet the timing requirement. When you want to interface character LCD with an AVR, you have to make these pulses with CPU. You have to write a code that changes GPIO pins status, and with delay function you can do the timing. Like this code that is written for STM32. An instruction specifies RS, RW and 8 data pins status. RW is always connected to ground because I'm writing to LCD. RS pin state is the input with the name state. Its type is boolean. And 8 data pins state is a byte name data. Its first input argument for this function. In this function, pin states are changed with HAL GPIO write pin. And timing requirement is met with microsecond delay function. In lots of MCUs, there is no dedicated peripheral for parallel communication, but you have to make these pulses somehow. You can use CPU, it's called software implementation. Because to do a task, you have to write software, write code, and CPU has to run that code. If you use peripherals, in this case timer and DMA, to make these pulses, CPU has to initialize peripherals one time. Then each time MCU sends an instruction, CPU just has to start the operation. This is called hardware implementation. RS pin is changed just at the start of operation, so CPU can change this pin. Problem is reduced to implement enable and 8 data pins. This is enable pulse and it can be generated with a timer output channel in PWM mode. I use timer 1 channel 1 and it is connected to E pin of LCD. For enable pin, on time is 15 microsecond and off time is 45 microsecond. This is bigger than the timing requirement because of instruction execution time. After enable pin is set, I have to put a byte on parallel bus by putting the byte on 8 data pins. After timer 1 channel 1 is set, channel 2 can send a DMA request. So DMA puts the byte on 8 pins. For MCU data pins, I choose PR0 to PR7. These pins are going to be in general purpose output push-pull mode. PR0 to PR7 of MCU is connected to data pin 0 to data pin 7 of LCD. To change output state of PR0 to PR7, I can write a word, a 32-bit value to BSRR register. For each instruction that I want to write to LCD, I have to store a word in an array in RAM before communication starts. During communication, DMA1 channel 3 is going to transfer one word from array to GPIO ABSRR register with each timer 1 channel 2 request. This is how parallel interface is implemented. DMA is transferring data and timer controls timing and enable pin. To control the number of instructions that I want to send, I have to control number of update events in timer 1. In timer 1 in 1 pulse mode, update happens RCR plus 1 times and then timer stops. RCR is the reload value for second counter in advanced timers, timer 1 and 8. Every time CNT counter overflows or underflows, repetition counter decrement by 1. Repetition counter counts from RCR register to 0. In advanced timers, update event happens only when repetition counter is going to decrement from 0. In this example, ARR is 6. It means CNT counter counts from 0 to 6 and then counter overflow happens. Repetition counter counts from RCR, which is 1, and it decrements by 1 every time counter register overflows. Here repetition counter is 1. After counter overflow it's 0. When it wants to decrement from 0, it's when repetition register is reloaded in repetition counter and its value is 1 again. This is when update event happens. In second example, RCR is 2 and update event happens every third time counter overflows. In one pulse mode, counter stops at the next update event. In this example, one pulse mode is activated and RCR is 0. Counter stops from 0 and counts to ARR. Then an update event happens and counter stops. In this example, one pulse mode is activated and RCR is 2. You know, in one pulse mode, counter stops at the next update event. First counter counts from 0 to ARR and one counter overflow happens. In this event, repetition counter decrement by 1 from 2 to 1. Next time counter overflow happens, it changes from 1 to 0. And next time counter overflow happens, when the repetition register is going to be reloaded in the repetition counter, that's when update event happens. And that's how I control how many instructions I want to send. To calculate ARR and PSC, first you have to decide values for counter period and counter clock period, green and red. You have to decide values for these two. I want my counter period to be 60 microsecond and counter clock period to be 1 microsecond. 1 plus ARR times 1 microsecond is 60 microsecond. So ARR is 59. And for CNT clock period to be 1 microsecond, PSC has to be 71. This is my starting point, a project named LCDI with CMCs. With this function, clock is set to 72 MHz, and this is for SysTick configuration and some other system initialization. There's a lcdi.c and lcdi.h file. Go in lcdi.c, write a function with the type of void named lcd_init. Input argument is void. I start by doing GPIO configurations. Pin PR0 to PR7 are parallel bus data pins. PR9 is RS pin and pin PR8 is enable pin. This is timer 1 channel 1 output. First, enable GPIO-A clock by setting bit IOPAEN in APB2ENR register. To set bit IOPAEN in APB2ENR register, I do bitwise OR assignment with bit mask. Pin PR0 to PR7 are in general purpose push-pull mode. Mode has to be 1, 0, so it's output mode with max speed of 2 MHz, and CNF00 general purpose output push-pull. 0, 0 for CNF and 1, 0 for mode. It's 2 in hex. To configure pin PR0, I have to configure bits mod 0 and CNF0, and for PR7, bits mod 7 and CNF7. So to configure all 8 pins at the same time, I can write this value in GPIO-A CRL register. GPIO-A CRL register assignment, and these are 8 twos to configure 8 pins. Pin PR9 is connected to LCD-RS pin and it's in general purpose push-pull mode. Mode 9 is 1, 0 and CNF9 is 0, 0. In this line I cleared mode 9 and CNF9 bits in CRH register in GPIO-A peripheral. In this line I set mode 9 bit 1. Mode is 1, 0 and CNF is 0, 0. Pin PR8 is timer 1 channel 1 output and it's connected to LCDE pin. This pin is in alternate function push-pull mode. Mode 8 has to be 1, 0 and CNF8 has to be 1, 0. In this line I cleared mode 8 and CNF8 bits in CRH register in GPIO-A peripheral, and in this line I set mode 8 bit 1 and CNF8 bit 1, and mode 8 and CNF8 are 1, 0. Timer 1 setting. First, enable timer 1 peripheral clock by setting timer 1 EN bit in APB2ENR register. Setting timer 1 EN bit in APB2ENR register. To have an upcounting counter, CMS and direction bits has to be cleared in CR1 register. Timer 1 CR1 register, to clear bits you do bitwise and assignment with not of bit mask. These are the bit mask for the bits that I want to clear. CMS and direction bits should be cleared in CR1 register. OPM bit in CR1 register has to be set so one pulse mode is enabled. Pay attention, in our case timer 1 is not going to count just one time, it's not one pulse, but timer is going to stop after a certain amount of update event happens, and I'm going to set that amount in repetition register. Timer 1 arrow operator CR1 register bitwise or assignment to set bits with bit mask. I want to set bit OPM in CR1 register. ARR is 59 and PSC is 71. Timer 1 arrow operator ARR register assignment casted 59 and for PSC register 71. I'm going to continue with configuring channel 1 and 2. This is calculating value for CCR1 register. I want timer 1 channel 1 output to have a 15 microsecond on time in a start of every 60 microsecond. One step duration is 1 microsecond, and I just have to find out how many steps are in 15 microsecond. So 15 divided by 1 is 15. To have a 15 microsecond on time in timer 1 channel 1 output, CCR1 has to be 15. This is calculating CCR2. 3 microsecond after timer 1 channel 1 output is set, I want channel 2 to send an interrupt request in this project, and in the next project a DMA request. I have to find out how many steps are in 3 microsecond. 3 divided by duration of 1 step is 3. CCR2 has to be 3, so 3 microsecond after channel 1 is set, channel 2 sends a DMA request. Timer 1 CCR1 is 15 and timer 1 CCR2 is 3. Channel 1 is in PWM output mode. First I have to enable preload by setting bit OC1 PE in CCMR1 register. Timer 1 CCMR1 register bitwise or assignment to set bit, setting bit OC1 PE. Next step is configuring channel 1 as output by clearing 2 bits of CC1S in CCMR1 register. Timer 1 arrow operator CCMR1. For clearing bits you do bitwise and assignment with not of bit mask. I want to clear bits CC1S. When you enable preload, channel shouldn't be in output mode. Here I write, instead of bitwise and assignment, I do bitwise or assignment with bit mask. So CC1S bits are set in CCMR1 register. I want a channel to not be in output mode, then I enable preload, and then channel is in output mode. This is the output that I want for timer 1 channel 1. If counter is up counting and channel 1 output is not inverted, if I want on time to be at the start of every timer 1 cycle, timer 1 counting, it has to be PWM mode 1. OC1M bit has to be 110 in CCMR1 register, so PWM mode 1 configuration is applied. Timer 1 arrow operator CCMR1 bitwise and assignment with not of bit mask. In this line I cleared 3 bits of OC1M. In this line I set OC1M bit 1 and 2. OC1M is now 110. Clear CC1P in CCER register, so channel 1 output is active high. Timer 1 arrow operator CCER register bitwise and assignment for clearing bits with not of bit mask. Clearing bit CC Timer 1 CCER register bitwise and assignment with not of bit mask, clear bit CC1P, and enabling channel 1 and channel 2 in CCER register by setting bits CC2E and CC1E. Timer 1 arrow operator CCER register bitwise or assignment for setting bit CC1E and CC2E. This was channel 1. Here I write channel 2. Channel 2 is in output mode and CC2S in CCMR1 register has to be cleared. Channel 2 is in frozen mode and OC2M in CCMR1 register has to be cleared. Frozen means I don't want an output pin for channel 2. I just want to use channel 2 to compare CCR2 and CNT register. When their value is equal, in this project channel 2 is going to send an interrupt request, and in the next project a DMA request. Because I'm using timer 1 and timer 1 is an advanced timer, to use output I have to set bit MOE in BDTR register. Next step is enabling channel 2 interrupt by setting bit CC2IE in DIER register. Before enabling any interrupt, you have to clear its flag. This is how I clear CC2IF flag in status register. And it's good to generate an update here. It causes the value to be saved in registers with preload capability. And because I'm generating an update event, it's good to clear update interrupt flag in a status register. You also have to enable capture compare to interrupt in NVIC peripheral. First, I define the variable of type uint32t to store priority grouping. Then with NVIC set priority, I want to set the priority for capture compare to interrupt. All timer 1 channels have one interrupt. It's timer 1 CCIRQ number. It's the interrupt number. First input for this function. Second input is priority, and I made priority with NVIC encode priority. Preemption priority is 3 and sub priority is 0, and PG is priority grouping. In the next line, enable interrupt with NVIC enable IRQ. This function has one input and that's interrupt number. Compile the code. There is no error and warning. Next step is writing callback function for capture compare to. Write the function with the return type of void, name LCD-CC2 callback, input is void. To specify this function as callback function for timer 1 channel 2, you have to write its address in a function pointer variable. I have defined a structure named x callback timer 1. This is a structure. You put dot after a structure, you can access its members. All of these are function pointers to store callback function addresses. I want to write address of capture compare to callback function. Then assignment. Then I write address of LCD-CC2 callback function in this function pointer variable. Compile again. This part is about changing RS and 8 data pin output state. Each output pin has an ODR bit in ODR register that represent its value. If ODR is 1, output is high. If ODR is 0, output is low. Because there is no atomic access on ODR register bits, I use BSRR register to change ODR. For every ODR bit in ODR register, there are 2 bits in BSRR register. BS bits are for setting ODR bits and BR bits are for clearing ODR bits. ODR 9 bit in GPIOA ODR register represent PR9 pin output state. To set ODR 9, I can write 1 to BS9 in GPIOA BSRR register. This makes PR9 output state high. To clear ODR 9, I can write to BR9 in GPIOA BSRR register. This makes PR9 output state low. To change RS pin, I'm gonna add 2 definition in lcdi.c. First one name is send data. To send the data instruction, RS pin has to be high. Writing 1 to BS9 bit in BSRR register sets ODR 9 bit and make PR9 output high. Second one is send command. When you want to send command, PR9 pin which is connected to LCD RS pin has to be low. Writing 1 to BR9 bit in BSRR register clears ODR 9 bit and makes PR9 output low. To put a byte on parallel bus, PR0 to PR7 output has to change. And ODR0 to ODR7 in GPIOA ODR register represent PR0 to PR7 output state. To set ODR0 to ODR7 in GPIOA ODR register, I can write 1 to BS0 to BS7. And to clear ODR0 to ODR7, I can write 1 to BR0 to BR7 in GPIOA BSRR register. Now imagine I have a byte. It has 8 bits and it's the value that I want to put on parallel bus. Least significant bit is PR0 output state. Least significant bit is 1, it means PR0 is high. And most significant bit is PR7 output state. If you want PR0 to PR7 output state to be like this, what is the value that you have to write to GPIOA BSRR register? Stop the video and think about it. If X is the byte, this is how you calculate the value that you have to write in GPIOA BSRR register. Before communication starts, I have to prepare words. Word is a 32-bit. To write to GPIOA BSRR register. I define an array with members of type uint32t. Its name is BSRR and it has 32 members. Every time capture compare to callback function happens, I have to write a new value to GPIOA BSRR register. To put a new value on pin PR0 to PR7. These are the values that I stored in BSRR array. I don't want a member of BSRR to be written in BSRR register over and over. So I need a counter here. And in the next line I have to increment counter by 1. For counter I define a variable of type uint8t. Compile the code. Next step is writing a function with return type of void. Name is bsrr prepare. First input is address of a byte. It's an array of bytes and its name is byte. Second input is number of bytes. This function job is to make a 32-bit word for every instruction byte and store it in BSRR array, so later it can be written in BSRR register. Stop the video and write this function. BSRR prepare function is just a for. Next step is writing a function to configure timer and DMA to send data instructions to LCD. First input of this function is address of first byte, and second input is the number of data instructions that I want to send. Write another function named LCD command. This function configure timer and DMA to send one command instruction. This function has just one input, instruction byte that you want to send. In send data instruction function, first I make P on 9 which is connected to RS pin high by using send data macro, and in send command instruction function with send command macro I make P on 9 output pin low, so LCD RS pin is low. This is for sending command instructions. Counter variable is index for BSRR array and it has to be zeroed before any communication starts. In LCD print function call BSRR prepare. First input is a string, first input of LCD print function, and second input is size, second input of LCD print function. In LCD command function, I don't need to call BSRR prepare because it's just one byte. Here I write the 32-bit value that has to be written in BSRR array with index of 0. I delete byte array here and I write command. In this line, for command byte, I prepared a 32-bit word and stored it in BSRR array with index of 0 to be written in BSRR register later. Last step in these two functions is enabling timer 1 by setting CEN bit in CR1 register. But when and how timer 1 is going to stop? In each timer 1 cycle an instruction is written to LCD, and I want timer 1 to stop after it sent my desired number of instructions. Stop the video and explain how timer 1 is going to stop. In one pulse mode in advanced control timers, timer 1 and timer 8, after timer is started, CNT overflows RCR plus 1 time. In this case 2 plus 1 is 3. 1, 2, 3. Then an update event happens and counter stops counting because it's in one pulse mode. In RCR register I have to write number of bytes that I want to send minus 1. Because number of cycle before timer stops counting is RCR plus 1. And for LCD command function, RCR is 0 because I just want to send one instruction. After you change RCR in both functions, you have to generate an update event because RCR register has preload capability and its value is not saved until an update event happens. When I want to send one or more than one data instructions, I can use this function. And when I want to send a command, I can use this one. After this line, timer 1 counter is activated and CEN bit is 1. After timer 1 stops counting, CEN bit is 0 again. So CEN bit is an indication if parallel bus is busy. When these two functions are called, if parallel bus is busy, I want to wait. In this while timer 1 CR1 register bitwise AND with CEN bit mask. Until CEN bit is 1, CPU is going to wait here. This function is also should be in a start of LCD print. Putting this while here is for safety, and if I write my code carefully I don't need this. There are also other ways to work around this problem, but I'm not gonna talk about it in this tutorial. To initialize LCD after power on, you have to send a specific commands with wait states. After that, you send function set and display on off control and int remote set command instructions. In lcdi.c file, change name of this function to lcd peripheral init. Write a new function with return type of void, name is lcd init, input is void. Call lcd peripheral init. Lcd peripheral init is for initializing GPIOs and timer 1. And this is the code to implement initialization process for LCD. To implement these waits, I used delay ms. This is a millisecond delay like HAL delay function. It's made with SysTick timer. I also have to add definitions to lcdi.h. These are definitions for instructions base value, and these ones are bit mask for configuration bits. Go to lcdi.c, compile the code. There is no error and warning. Next step is writing a function with return type of void named lcdSetCursor with two inputs of type uint8t. Before I write a character to character lcd, I have to specify which character space I want to write this character to. This function is going to do this for me. This function is a switch with two cases. Compile the code, go to main.c, call lcd_init function, compile the code. There is one warning, and that's because I forgot to write function declarations in lcdi.h file. Now compile again, go to main.c. After lcd_init, call setCursor function. I want my first character to be written in row 1, column 1, character space. Before main, I define a global string named AA. And now after lcdSetCursor, I call lcdPrint function. First input is address of a byte. Its type is uint8t asterisk. I'm casting first input. Its value is going to be AA. I want to write this string to character lcd. Second input is number of bytes that I want to write. For second input, I write size of AA. Compile the code. This is blue pill and this is character LCD. PA0 to PA7 are connected to data pin 0 to data pin 7 of a LCD. Enable pin is connected to PA8 and RS pin is connected to PA9. RW pin is connected to ground. I want to write pointer X in character LCD in column 1 and row 1 here. Compile the code and load it in MCU. Look at LCD. I wrote pointer X in character LCD, but there is an additional character here. To fix this, I just have to subtract 1 from size of AA. Stop the code and explain why I have to do that. Compile again and run again. Now I want to write pointer X in row 2 and column 1. Compile again and run again. In LCDI project, I used interrupt to write values in BSRR register. In the next step, I want to use DMA. Make a copy of LCDI project. Right click and paste. Name it LCD DMA. Right click on LCDI, click close project. In LCD DMA, core, source, main.c, go to project, properties, C++ general, paths and symbols. You have to edit these 3 directories. It's LCD DMA. Go to lib folder, right click on lcdi.c, rename, name it lcddma. Right click on lcdi.h, rename lcddma.h. Delete debug folder and lcdidebug.launch. Compile the project, there is no error and warning. Go to lcddma.c. Next step is using DMA to transfer data to BSRR register instead of doing it in capture compare to callback function. Delete this function. In LCD peripheral init function, I don't need to enable interrupt for capture compare to anymore. Instead, I have to enable DMA request. To do that, I set bit cc2de in DIER register to enable DMA request for timer 1 channel 2. There is no capture compare to callback function anymore. Delete this line. And there is no need to enable interrupt in NVIC peripheral. There is no need to clear cc2if and UIF flags in status register. Delete this line. After this, I have to do DMA configurations. In STM32F103, there is just one DMA peripheral. It's DMA1. First step was enabling capture compare to DMA request in timer 1 by setting bit cc2de. Next, I have to enable DMA1 peripheral clock by setting bit DMA1EN in AHBENR register. RCC arrow operator AHBENR bitwise or assignment to set bit, and this is bit mask for DMA1EN bit. This is DMA1 request mapping. It shows connection between peripheral request signals and DMA channels. My DMA request is coming from timer 1 channel 2. It's connected to DMA1 channel 3. This is how I know what channel I have to use. Each DMA channel has a CPAR register. It's a peripheral register address that DMA channel is going to read from or write to. In this case, I want to write to BSRR register in GPIOA peripheral. So I write address of BSRR register in DMA1 channel 3 CPAR register. In comment, I add DMA1 channel 3. DMA1 channel 3 arrow operator CPAR register address of GPIOA BSRR register. Compile the code. There is one warning about this line. It says this line makes integer from pointer without a cast. Stop the video and solve the problem. This expression type is uint32t asterisk. This expression type is uint32t. That's why there is a warning. To solve the problem, you cast the pointer. Compile again. There is no warning. Each DMA channel has a CMAD register. Its memory address that DMA is going to read from or write to. In this case, DMA is going to read values from BSRR array. DMA1 channel 3 arrow operator CMAR register assignment. Don't forget to cast it. And this is address of BSRR array. DMA is going to transfer words from BSRR array to BSRR register. Every DMA channel has a CCR register. It's channel configuration register. First, I'm going to write 0 to CCR3. DMA1 channel 3 arrow operator CCR register assignment 0. Mem to mem bit is 0. Priority is not important. And I put priority to low. 00 for PL bits. M size is the size of data that DMA is going to read from memory or write to memory. In this case, DMA is going to read 32-bit values from BSRR array. M size has to be 10. P size is the size of data that DMA is going to read from or write to peripheral. In this case, DMA is writing 32-bit values to BSRR register in GPIOA peripheral. P size has to be 10. I have to set minc bit to enable memory increment mode, because I don't want DMA to read the same value from BSRR array. Pinc bit has to be cleared to disable peripheral increment mode. It means I want to always write to same peripheral address. It's BSRR register address. Circular mode is disabled. Direction bit has to be set because I'm reading from memory from BSRR array, and all interrupts are disabled. DMA1 channel 3 arrow operator CCR register bitwise OR assignment for setting bits, and these are bit masks for bits that I have to set in CCR register for channel 3 in DMA peripheral. Go to LCD print and LCD command. After checking busy flag, channel 3 DMA1 by clearing EN bit in CCR register. Do this for LCD command also. In both functions, before enabling timer 1, enable DMA1 channel 3 by setting EN bit in CCR register. Do this for the LCD send command too. For DMA1 channel 3, I have to write number of data transfers to CNDTR register, its size, second input for this function. And for LCD send command, I just want to write one instruction. DMA is going to transfer just one data. I write 1 to CNDTR register. For DMA1 channel 3, go to main.c, compile the code. This is my blue pill and this is character LCD. Compile the project and run the project. In the last project, I wrote pointer x here. Now I want to write it in row 2 column 6. Compile again and load the project. You see pointer x is written here. Go to main.c. Instead of pointer x, I want to write STM32 F103 C8. I want to write it in row 1. Compile again and load the project. You see STM32 F103 C8.